Our final speaker for this session is Mr. Heinrich Greeff, who recently joined Reutech Mining. Heinrich will be discussing the automation and design process of the design process and Reutech Mining. Paul, you mentioned mining the ocean. I think Heinrich is going to show you an alternative to mine. Anyway, thank you very much. Welcome, Heinrich.
Yeah, good morning. Hope you're all enjoying the session so far. I was trying to keep my concentration earlier with Paul and Rian. After they start speaking or they spoke, gears start turning in my head. So I think I might have forgotten some of the stuff I wanted to tell you guys. But I think it actually adds very nicely into their presentations. I spoke to Rian last night, and this month is actually the 12-year anniversary of him hiring me into mining. I was studying Astro Physics at the University of Potchefstroom, and they came to recruit people for rock engineering at that time. I think paper one was quite difficult at that point, and they had people struggling to get through the mathematics side of it. And I remember I spoke to my mum after I'd gotten the job, and she's like, "Hein, you studied the stars and now you go work in a hole." And I was like, "Mum, just wait, you have to go down before you go up." So the question is, what does a candle, a canary, and the moon all have in common? And I've kind of led you to the answer. It's mining. So up until the point in 1850, we'd been using candles underground as a light source. And the candle itself wasn't really the innovative part. It was the candlestick that they used. So this candlestick had a hook on it so that you could hook your candle on a ledge while you were busy working or digging using your pickaxe in those days. It also had a spike that you could use to hammer it into framing timber, and then had a ring that you could obviously use to carry it on a hat. And then in 1850, things got better and they started using oil lamps, like you see in the photo. And I don't know if you guys have seen the photos where the guys are covered in soot, and I always thought they were coal miners. And when I was doing research, I found out that it's actually these oil lamps that they were using that had so much smoke coming off them that the guys cover themselves in soot working there. And then in 1915, the Americans approached Thomas Edison at the time and said, "Listen, surely there can be a better way." And at that point, they invented the flameless electric miner's lamp, flameless being the funny part of it, right? It was amazing to have a light source on the ground that didn't have a flame. Good. And then you guys know the story about canaries. What surprised me about it was that I was already 2 years old by the time we finally switched over to the electronic nose. Up until that point, we were still using canaries to check for poisonous gases, carbon monoxide. And it was John Scott Haldane that actually also on the side of innovation understood how nature worked, and he described it as a one health system in mining at that point, saying that look at the cockroaches, look at the rats, look at other organisms around you to decide whether or not your mining environment was actually conducive to, well, life and to miners down there. And that's where the canary came in. And then, so this is a Wikipedia reference, but as early as 2025, they're planning on starting to mine the moon. It's actually current updated data following COVID is that it will take another 30 years. What's interesting about mining the moon is that they're planning on mining helium-3 on the moon. So helium-3 was a radioactive isotope that was discovered in 1939. And it's a form of clean nuclear energy, or we can source clean nuclear energy from it. And there's about 1 million tons of it on the moon. So it's the dust that covers the moon that's ionized by the sun, being not filtered by the atmosphere. And on Earth, we only produce about a few kilograms of helium-3 every year, whereas, like I said, on the moon, there's about 1 million tons. Each ton of that is worth about $3 billion US dollars. The payloads that they're planning on bringing back from the moon is, I think, about 25 tons per payload. And after we've mined about 25% of that in the moon, it could very well power Earth for the next 500 years, which is quite amazing. The interesting part about this is the timeline, obviously. I mean, in 1915, we started using electric lamps in mining, and 110 years later, we're planning on mining the moon. That all was to kind of prepare you guys for the fact that automating the design process isn't necessarily that far into the future. Good. Right, so we'll go through the engineering design process as we currently know it or have known it for the last 40 years. I'll give you an overview of what has been automated up to this point or what are the chances of it being automated. We'll speak about the rock engineering design process. It's quite fortunate and lucky to have both Rian Carstens and Jannie in the audience because I'm going to be showing their rock engineering design processes. And then we'll talk about the rock engineering design process in terms of what can and what should already be automated in these, how will this change things in mining, and then lastly end off in a similar fashion to what Paul did with, what is required to make this happen, and then what will Reutech Mining's role be in it. Good, so I trust you guys are all familiar with this process. I was trying to find a better way to explain it to you guys. So I figured I would use the taco example. So the example is, I'm hungry, I want to find something to eat. Doing my background research means I open up my fridge and it's like, heck, I can make tacos. There's, out of all of these ingredients, something could work. So you start specifying your requirements in terms of are you going for a savory or a tangy or a sweet taco. You evaluate and provide some solutions by playing around with some of the combinations that you think might work. If you have mayo, it obviously opens up the door. And then you start testing some of your solutions. You make small batches or you test 2 ingredients together. And then you start building a taco and then communicate your design back to the rest of the house and let them all know we're going to eat tacos. And in a similar way, the engineering design process has elements of it that has already been automated. Like Rian said, it's once you have everything in a digital format, and those digital formats can from one software package carry over onto the next software package, you have steps in your design process which effectively have become automated. Process through available technology. If you think about developing and testing a solution, that's where 3D printers brought in huge advances in terms of how quickly can you develop this. I put in this question about numerical skills for engineers. And I think for the rest of the presentation, I'm almost going to shy away from using the word engineer in the engineering design process, because I think because most of the calculations and most of the heavy thinking part can now be replaced by computers, or going forward be replaced by computers. And I think the people that we are going to be using in future to conceptualize designs, this designer of sorts, must understand the software packages better, must understand the limitations of the software, and then obviously understand how these packages will work. And I'll probably reference back to it later on in the presentation, but I think it's going to draw in people from different areas of our civilization. Up to now, I mean, mining and all of this, if we just look at this audience, I mean, we can almost pull a line through the personalities in here. And I think we're going to start pulling in different people when we start looking at automating the design. Good. And all of that is to say that training is due to change. If we're going to look at automating the design process in the way that the guys will carry on, what they need to know and understand will be different. So if you've ever had a class from Jannie Maritz, you will recognize the slide. He gave me a few options of his slide 1, as he colloquially calls it. I chose this one just because I think it has quite a bit of character in it. So for the rock engineering design process for underground, you start off by, in this rock engineering design process, defining your stress field. You go through some calculations, you determine how will your rock mass fail. After you've determined your rock behavior, you look at how to achieve stability, and it all ends with beer and happiness. Good. Then this is Rian Carstens' rock engineering design, and you can see that Rian starts off with defining the mine environment, ground conditions, loading conditions, failure mode, similar to what Jannie did. And then Rian spends quite a bit of it on risk assessment, and then it moves on to support design, implementation, optimization. And exactly like what Rian said was, I kept the color the same between the bottom and the top part because they're not that different. Once you start acquiring data for your design, you never stop acquiring data. And the fact that you get to the bottom where you're trying to optimize or implement your design doesn't mean that you neglect what you did in the beginning. It all has to tie back in. And the reason why I chose these two rock engineering design process is to show that even though the two rock engineers are here and they are both very good and well recognized, they have different ways of, just get this to play. They have different ways of doing the same thing. They arrive at the same point, but in their own style and fashion. That's true for all rock engineers. And that in essence is why the engineering design process hasn't yet been automated. So design does not refer to the physical skills of the engineer or the person doing it. It refers to that intellectual part of the design, that the part where you feel comfortable with what you've designed. If we automated the design of this room, if we handed over the design of this room, the chairs, the tables, the bags, the lights to a computer, the focus points might have been on efficiency or whatever we programmed into the algorithm. But the fact that this room and the way it feels was designed by a person for people is what gives it that personal flavor. That being said, so what can and what should be automated? Like I said, anything to do with the mathematical modeling or the numerical calculations at this point can be automated. If you already know which formula you're going to be using, how you want to use it, if you have accurately defined your input parameters, a computer will more reliably do that calculation. There's no need for us to hand bomb it anymore other than the joy you might get out of it. Processes can be integrated into a single seamless process or combining separate design functions. And here, like I mentioned earlier, if you have software packages, when your data is already digitized and these software packages feed into each other, you can have a single seamless process. In other words, you can input your design parameters in the beginning and it keeps on popping out an answer, and you can change small things, but that process is automated for you. Repetitive or tedious tasks in the design process. There are a bunch of these examples in rock engineering design where you almost copy and paste just because you know how repetitive this process is, and that's obviously where issues might come in. And then updated design. So once a design has been done, you've defined your input parameters, and one of the input parameters changes, you should be able to change that input parameter and the whole design is updated instead of going through all of those calculations again. And then the last one refers back to the video we just saw. It's if we start automating parts of this design process and you don't have to go through that iterative part of it, you can sit back and try and find a creative solution to it. There are different solutions. The fact that we're planning on mining helium-3 off the moon is an example of the fact that we are almost seeing ourselves as well, not seeing it, but moving towards that direction of being a multi-planet species as humans. That we're saying that Earth is a finite environment, and in order for us to survive here, we start looking at energy sources from other planets. It almost sounds like in these alien movies. Good. And at the risk of stating the obvious here, I'm going to talk about the influence that food had on the progress of civilization, and then try and tag it back into the effect that automating the design process could have on our rock engineering designs. So in the beginning, everybody was hunter-gatherers. Let's assume that is the starting point here. And from the moment you wake up till you go to bed at night, you worried or you thought about what were you going to eat today. And next morning, rinse and repeat. You do all of it over again. And it was the hunter-gatherers who already had enough to eat that made the shift over into farming. But up to that point, I mean, if you were a farmer but you needed to be hunter-gatherer, it was useless. And as food was grown and stored more efficiently, populations increased and settlements grew larger, creating both the incentive and the means to produce even more food. And then the last one is where it gets interesting, to say that in the two-way circle of growth, populations, food production, as that kept on increasing, so did the technology. In other words, the way in which we mined. And like I said, at the risk of stating the obvious, I think as these people could not have seen, as we could not have seen how civilization would have progressed as we started finding better ways to produce food or even cook food to make it more nutritious. In that same way, I think the engineering design process, once it starts optimizing, might open up completely new possibilities. So we have a faster design process. Like I said, parts of it is already automated. You can just define your input parameters. And if these input parameters are monitored correctly, that you don't input the values yourself, but that they're recorded and inputted into software directly, it just speeds up that process. The ability to enhance the design to a new level, error reduction because you don't have to do the readings manually, multiple design options at the click of a button, just meaning that there are multiple options, there are multiple ways of doing a design, and then including variables for a more complex design. So you can include stuff that previously, Rian spoke about the joint sets and the geological structure. At this point, we don't clearly define that structure yet, and we almost, I would say, shy away from defining it because it becomes so complex. At some point, you have to kind of step back. The idea is that once we've started automating it, we can start including more things. And then integration of analysis, design, drafting, and scheduling. If you have your design process automated, it becomes easier in the beginning to say, these are the input parameters, this is what the design needs to look like, and what is the equipment that will eventually be mining this design. That right from the beginning to the end of this whole project or the mine, the whole process is integrated, and you can almost back analyze. You say, well, I only have this equipment to mine, therefore everything else in my design needs to add into it. If you think about the moon is such a nice limiting factor, we won't necessarily have people on the moon. It'll be machines and robots, and you have to mine all of it through a computer screen, and it's a limiting factor that's at the end of the equation. But once you've automated, you can bring it back from that end and work your design backwards. And then automation of the physical processes. The best example I could think of while I was coming up with food ideas was spit fry. I mean, it happens, right? And then problems associated with automation, it's obviously not all just rosy colored. So one of the big things is that the risk of error alters significantly. The fact that you have software packages or applications talking to each other means that a mistake can be made during your input parameters, but it keeps on being carried over through different software packages. It makes it difficult to detect it. Complexity of designs. Your own design might become very intimidating to you. Like you might see the answer and you think, well, that's the answer. I'm not going to argue with it, but it's just because the design became so big. And then unanticipated or unrecognized consequences. Peter earlier spoke about it. I'm sure if he now encounters a mine again where there's water anywhere in close proximity, he immediately is like, listen, I've got a little photo book I want to show you of how this can go wrong. And if you've done a mine design for a dry mine and you enter water as a change in your input parameters, it's not that you can go one step back and say, okay, cool, I have to design for water. It means that the entire mine design might have to change. And that is one of the risks with automating this. And then error will continue, but the cause and type of error changes. If we now, in these days, review a geotechnical design, it's almost easy to pick up the telltale issues because you know what to go look for, you're familiar with it, you have a feel for it. If the process has been automated and a computer is doing part of this, it becomes more difficult to track down those changes. It's not to say that the one is better than the other, but it's just to say that be cognizant of the fact that cause and type of error has changed. And then black box syndrome, the false confidence you get from the fact that a computer has given you an answer. I mean, we can Google stuff, and even though it was entered by a person, just the fact that you've read it on Google, gives you confidence. I mean, that's where the whole concept of fake news comes from, right? So what is required to make this change? We spoke about that in the beginning, saying that education and training changes. If we're not going to be looking at a typical engineer anymore, but a person that has a better conceptual or holistic view of the design process and how this all fits together, Important to keep the complete picture in mind, a holistic view of what you're trying to do. And then tying back to what Rian mentioned, accurate design input parameters and accurate monitoring of the, to confirm these input parameters is basically what it rests on. You can't start automating or you can't start modernizing your design if your input parameters aren't correct. And that then is where Reutech positions itself, to say that the company in the years going forward would like to partner with companies, get an understanding of what these input parameters are, and develop the technologies necessary to automate these processes. So as my ending slide, I'd like to, as we go into the panel discussion, open the discussion for design input parameters. So there are physical and non-physical design input parameters. I've listed, I think, the 3 physical design input parameters that we're familiar with. You look at the stress state of your rock mass, and you're going to look at, say, virgin and induced, quasi-static or dynamic, whatever that environment is that you're operating in. The material properties being the strength and structure of it. And then ultimately, the only thing that we actively measure is movement. We determine stress back from movement in the way that the rock reacts. But like I said, for the panel discussion, I'd like to keep that up there. Good, thank you.